Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is air preparation in pneumatic systems. Our objective is to examine how ordinary environmental air is transformed into the power transfer medium of choice central to pneumatic systems. We'll examine filters, lubricators, regulators, compressors, prime movers, pressure switches, relief valves, and more. Additionally, we'll examine how pneumatic systems regulate pressure inside the receiver and the circuit itself. This lecture operates under the presumption the viewers watch the complete hydraulics playlist and the Introduction to Pneumatics lectures, all available at the Big Bad Tech channel. If you haven't watched these lectures yet or only dimly recall their contents, please take the time to do so now. Again, the pneumatics playlist is a bonus round extension of the existing hydraulics playlist and presumes you have a familiarity with hydraulic components, schematics, and theory of operation. Before we begin, I need to say this is actually one of the most difficult lectures I've ever scripted. And believe me, I've scripted quite a lot of lectures, not because the subject matter by itself was difficult, it's actually quite easy, but rather because air quite literally touches every aspect of pneumatic systems. For this reason, it was hard to know where to start, and even more difficult, when to stop. In the interest of forward progress, I decided to restrict this lecture to a somewhat limited scope that I'll come back later to correct and expand upon when it's appropriate to do so. Let us begin. Perhaps the easiest way to discuss air preparation in pneumatic systems is to compare and contrast it with how oil circulates through a hydraulic system. On a very basic level, one can think of a hydraulic system as a series of power conversion stages. A prime mover converts one form of power, in the case of motor electrical, into rotating mechanical power with a measurable torque and rotational speed. The incoming rotating mechanical power from the prime mover is converted by a pump into hydraulic power with a measurable pressure and flow rate. Lastly, valves and accessory components route pressurized flow to actuators, which convert hydraulic power to mechanical power. In the case of hydraulic cylinder, a certain linear force at a measurable speed. Additionally, one might encounter rotating hydraulic actuators like hydraulic motors, the dirty, nasty, oily, greasy beasts they are. In summary, a prime mover converts electrical power to rotating mechanical power, a pump converts rotating mechanical power to hydraulic power, and an actuator converts hydraulic power to mechanical power. On a very basic level, pneumatic systems perform the exact same series of power conversion operations, albeit with different actors playing different roles. Notably, a compressor takes the place of a pump. The schematic symbol for a pneumatic compressor is almost identical to that of a pump, the one difference being the output arrowhead is clear rather than solid. Similar to a hydraulic system, a motor prime mover converts electrical power to rotating mechanical power. A compressor converts rotating mechanical power to pneumatic power, and an actuator converts pneumatic power to mechanical power. In the case of a pneumatic cylinder, linear mechanical power. Although extremely similar at this conceptual level, important differences between these two types of fluid power systems exist. A hydraulic system, quite like the human circulatory system, is closed, in that the oil sucked up from the reservoir via the pump is routed throughout the system, ideally with minimal leakage, and then returned to the same reservoir, typically through a return filter, where it's sucked up once again and rerouted through the same system over and over. Consider this simple hydraulic circuit. When the directional control valve is shifted to the straight-through position, the pump sucks up oil from the reservoir and pushes it into the cap end of the double-acting cylinder. As the cylinder extends, oil from the rod end is exhausted back to the reservoir. When operator releases the manual actuator, the spring offset directional control valve returns to the cross-connect position. The pump sucks up that same oil from the same reservoir and pushes it into the rod end of the double-acting cylinder. As the cylinder retracts, oil from the cap end is exhausted back to the reservoir. In summary, oil doesn't leave a closed hydraulic system. That's a good idea. Oil is dirty, expensive, and presents contamination, slip, and fire hazards. A pneumatic system, in contrast, is open. Why go to the trouble of storing and reusing air when we're quite literally immersed in air? Just suck up some more air when you need it and spill it back into the environment when you're done with it. There's no need for a return path or a dedicated reservoir in a pneumatic system because the entire surroundings effectively serves as a reservoir. Consider this extremely simplified pneumatic circuit consisting of a compressor, a directional control valve, and a double-acting cylinder. You note the directional control valve has two exhaust ports, identified as empty arrowheads pointing away from the system. These are exhaust ports that are open to the atmosphere. We'll examine the idiosyncrasies of pneumatic directional control valves in greater detail in later lectures. However, the same principles as hydraulic directional control valves hold true. Directional control valves in pneumatic systems similarly stop, start, and change the direction of fluid flow. When an operator shifts the directional control valve into the position on the right, the compressor sucks up air from the external environment and pushes it into the cap end of the double-acting cylinder. As the cylinder extends, air from the rod end is exhausted back to the environment. When an operator releases the manual actuator, the spring offset directional control valve returns to the position on the left. The compressor sucks up more air from the external environment and pushes it into the rod end of the double-acting cylinder. As the cylinder retracts, air in the cap end is exhausted back to the environment. In summary, air enters and exits an open pneumatic system. It makes sense. Air is cheap, clean, and doesn't present contamination, slip, or fire hazards. Lastly, there's an important difference how pressure is managed in these two different types of fluid power systems. Again, consider the simple hydraulic system consisting of a reservoir, a motor-driven pump, a pressure relief valve, a directional control valve, and a double-acting cylinder. You'll note the pressure relief valve is normally closed. When the motor turns the pump pulls oil from the reservoir and circulates it throughout the system. As long as the pressure is below the cracking pressure of the pressure relief valve, the pressure relief valve remains closed and oil flows through the hydraulic circuit. If, however, the cylinder reaches the limits of extension or retraction, the normally closed pressure relief valve opens and spills oil back into the reservoir, thereby limiting system maximum pressure. Lacking a pressure relief valve, system pressure could rise to potentially catastrophic levels. In summary, hydraulic systems largely limit maximum pressure using a single component, the pressure relief valve. In order to prevent damage or catastrophic failure, pneumatic systems must also limit system maximum pressure. However, they do so in a radically different manner using numerous complementary components, each with their own method of operation and area of responsibility. Allow me to demonstrate. As I alluded to earlier, I struggled scripting this lecture because air preparation touches so many aspects of pneumatic systems that it would be very easy to overwhelm a viewer new to the topic with some massive schematic with tons of new components right up front. After more false starts and rewrites than I'd like to admit, I decided to start small, illustrating only the most essential components in their simplest form, and add complexity and variation as we move along. This being said, by the time I wrap this lecture up, we will be looking at a pretty involved diagram. So if you're not warmed up already for the heavy lifting that's about to come, you might want to knock out a couple jumping jacks and groin stretches before we get to work. I think the simplest way to begin is to restrict our initial analysis to the 5 most essential elements, being the mechanically coupled motor and compressor, the receiver or tank, the pressure switch, and finally, the regulator. As we discussed earlier, the motor prime mover drives a compressor via coupling, illustrated schematically as a dashed line, which allows the motor and compressor to be taken apart for repair and service, as well as compensate for misalignment. The compressor converts the mechanical power of the motor to pneumatic power in the form of pressurized air with a given flow rate. Rather than routing air directly into the pneumatic circuit, as in our previous simplified diagrams, the compressor instead routes compressed air into a receiver, or a tank, a sealed metal housing schematically represented as an oval. A pressure switch on the receiver senses pressure inside the receiver. Lastly, a regulator selectively opens and closes the passage from the receiver to the pneumatic circuit. We'll return to describe in detail the operation of the pressure switch and regulator after we've taken some time to identify these 5 main components on a small rollabout compressor you might find at a construction site or a light-duty pneumatic system. The receiver is the horizontal tank. A reciprocating piston compressor is mounted on top of the motor prime mover. The pressure switch sensing pressure in the receiver is this plastic box. Lastly, the regulator is this adjustable valve. You note this compressor has 2 pressure gauges, one in close proximity to the pressure switch, sensing pressure in the receiver, and another in close proximity to the regulator, sensing pressure in the pneumatic circuit. Let's include these 2 pressure gauges in the diagram. Again, this one in the receiver senses pressure in the receiver, whereas the one next to the regulator senses pressure in the pneumatic circuit. Alright, now let's take a look at the pressure switch in a little bit more detail. On a very basic level, the pressure switch serves as the primary feedback to the motor about the status of pressure in the receiver. Based on this feedback, the pressure switch selectively starts and stops the motor. I'm illustrating this feedback as a simple arrow. However, it's a little more complicated than that. For those interested in ladder logic used to stop, start, and protect motors, I'd recommend checking out the Motor Control playlist, available at the Big Bad Tech channel. Today's lecture will primarily focus on the pneumatic aspects of the system, but will hint at these closely associated topics. The pressure switch is an electromechanical device, meaning it has both pneumatic and electrical schematic symbols, and will appear in both the pneumatic schematic and the ladder logic diagram controlling the motor. The pneumatic schematic symbol shows the passage used to measure pressure and a pair of normally closed and normally open contacts, as well as a slanting arrow indicating it's adjustable. If the pressure switch appears in a ladder logic diagram, the electrical schematic symbol is a switch with a semicircle hanging off the bottom. Here's an example of a mechanically interlocked pair of normally closed and normally open pressure switches with a common terminal. As hinted in the schematic symbol, the pressure switch consists of a flexible disc used to sense and measure pressure changes. As pressure builds, the disc is distended and closes or opens the associated electrical contacts based on the set and the reset values, where the differential between the set and reset is called span, among other titles. When pressure rises above the set value, the electrical contacts change states, i.e. the normally closed side opens and the normally open side closes. If, however, pressure falls below the reset value, the electrical contacts return to the original states, i.e. the normally closed side recloses and the normally open side reopens. Importantly, the motor starts and stops based on the state of the pressure switch electrical contacts. Below the set value, the motor prime mover drives the compressor to fill the receiver. If pressure in the receiver rises above the set value, the pressure switch turns the motor off. If pressure in the receiver falls below the reset value, the pressure switch restarts the motor and drives the compressor to refill the receiver back up to the set value. In this fashion, pressure in the receiver ideally should bounce back and forth between the set and reset values, i.e. it stays inside the span. Span is desirable because it prevents switch chatter at pressures around the operating point. Additionally, span prevents excessive and frequent starts and stops of the motor prime mover. Pending construction of the pressure switch in question, sometimes both the set and the span values are adjustable. This start-stop style of compressor control is the simplest and most popular, but by no means the only method of control. We'll examine compressors and compressor control in greater detail in later lectures. In summary, the pressure switch monitors pressure in the receiver, and it starts and stops the motor based on this information. In an ideal circumstance, pressure in the receiver would stay inside a predictable span. Let's now take a look at the regulator. To use the single term regulator actually does a disservice to this vital pneumatic component's dual roles. It might be more appropriate to call this a relieving or a venting regulator. Let's deal with the regulator function first. The regulator function can be schematically illustrated as a normally open valve passage pointing from the receiver to the pneumatic circuit sensing pressure on its outlet. A spring with a slanting arrow indicates the regulator is adjustable. Oftentimes a regulator also features a locking sleeve or a push-down pull-up locking knob that allows a technician to adjust the desired pressure value and lock it in place in the vain attempt an operator doesn't take it upon themselves to screw it up. A regulator's mission is to maintain the pressure of the pneumatic circuit inside a specific level by opening and closing the passage from the receiver to the circuit. If pressure in the circuit is below the set value of the normally open regulator, the regulator remains open and pressurized air from the receiver flows into the pneumatic circuit. If, however, pressure in the pneumatic circuit rises to the set value of the normally open regulator, the regulator closes, thereby limiting and maintaining a relatively constant pressure in the pneumatic circuit. If pressure in the pneumatic circuit falls below the reset value of the regulator reopens and allows pressurized air from the receiver to enter the pneumatic circuit. In this fashion, the regulator maintains pressure in the pneumatic circuit inside a given range. If you think about it, the regulator is acting similarly to the pressure switch. The differences being the pressure switch maintains pressure inside the receiver inside a predictable range, whereas the regulator maintains pressure in the pneumatic circuit inside a predictable range. Besides area of responsibility, another fundamental difference should be emphasized. The pressure switch is an electromechanical device that starts and stops a motor, whereas the regulator is a purely mechanical valve that opens or closes a passage from the receiver to the system. I should note during system shutdown, it's a recommended practice to readjust a regulator back to the minimum to relieve spring pressure on the valve and adjustment mechanism. At system startup, one will readjust the regulator back to the desired value and begin operation. Any competent lab instructor will make sure you check if you follow these procedures and take it out on your hide if you don't. Let's now upgrade our simple regulator to a more sophisticated relieving regulator. Schematically, a relieving regulator, sometimes called a venting regulator, is illustrated as a bidirectional valve with a double-headed arrow and an exhaust port back to environment. I should note, sometimes you might see a muffler or a silencer on the vent port, schematically represented as a zigzag maze-like passage. The muffler reduces the sound of the exhausted air. As previously, the arrow pointing left to right is the regulator function and operates as previously illustrated. If pressure on the output is below the set value, the normally open regulator remains open, permitting passage from the receiver into the circuit. If, however, pressure on the output rises above the set value, the normally open regulator closes, blocking passage from the receiver to the circuit. The arrow pointing right to left, in contrast, is the relieving function. In the event of some back pressure or pressure intensification event above the set value happens inside the pneumatic circuit, this passage open and vents excess pressure back to the environment. Once the pressure in the circuit subsides, the relieving passage recloses and the regulator continues to function as previously. Before we add anything more to this basic diagram, it's important to note that the receiver essentially acts like a pneumatic battery, being a stored quantity of pressurized air just waiting to be put to use. The motor and compressor charge up the battery at the direction of the pressure switch. The pressure switch additionally prevents the receiver from being overcharged by stopping the motor when it's appropriate to do so. The regulator, in contrast, draws down the stored energy in the receiver based on the needs of the pneumatic circuit by selectively opening and closing the passage from the receiver to the circuit. In the event of the pneumatic circuit experiencing a pressure intensification event, the relieving function would vent it back to atmosphere. Now that we've got an idea of how the motor, compressor, receiver, pressure switch, and relieving regulator work, let's examine some additional elements you might encounter in close proximity to the receiver, notably a safety relief valve and the manual dump or drain valve. The safety relief valve is a normally closed valve that senses pressure on its input. In ordinary circumstances, this valve remains closed. If, however, pressure inside the receiver rises above the set value of the safety pressure relief valve, let's say because the pressure switch fails to stop the motor, or some other equally bad overpressure event, the safety pressure relief valve opens and vents the excess pressure in the receiver to atmosphere. Another important accessory component in close proximity to a receiver is the manual dump or drain valve, schematically represented as a pair of opposing triangles. As we'll learn in later lectures, changes in air volume results in change in pressure, temperature, and air's moisture carrying capacity, among other properties. The manual dump valve might be actuated at the end of the day or during periodic maintenance to remove accumulated moisture or impurities. More sophisticated systems might use a solenoid-actuated dump valve that does so automatically on a specified interval. Additionally, a dump valve might be used to completely evacuate the reservoir as part of lockout and tagout procedures to ensure a system is safe to work on. Here's the safety relief valve from our earlier example system. Maintenance procedures may call for a technician to manually actuate the safety relief valve on a periodic basis to ensure it works properly. Good luck getting it to reseat properly after doing so. Ask me how I know. The safety relief valve can also be triggered accidentally by snagging on a hose or a power cord or bumping it while you're trying to work on something delicate inside a dimly lit enclosure. Again, ask me how I know. If we flip the unit over, we see the manual dump or drain valve. When open, this valve empties the receiver along with any accumulated moisture and contaminants, often intermittently freezing shut as it does so. I'll explain why this volume and pressure-induced temperature change occurs when we examine the combined gas law in later lectures. Speaking of contaminants, let's take a look at filtration. As you're no doubt aware, everyday environmental air is chock full of a shitstorm of dirt, dust, debris, boogers, and bug parts that don't belong in pneumatic systems characterized by dynamic seals with close tolerances. Pneumatic filters, similar to hydraulic filters, are made out of closely spaced mesh material designed to exclude certain size contaminants. Clean air, free from contaminants, is necessary for the smooth, leak-free operation of valves, actuators, and other pneumatic components.